All right, our topic for today is contradiction and contraposition. These are two different techniques, two similar but different techniques, and let's illustrate both of them carefully. So generally, contradiction rule works the following way: if P is a statement, and then from not P we derive contradiction, then we can conclude P. Generally, the idea behind this method of proving is that generally instead of proving given statement P, we assume negation of that statement. And then using correct logical reasoning, we try to get contradiction, which is in mathematics always considered like a trouble. So we say, you see, that assumption that negative P got us into trouble tells us we better not assume negative P, it is P. Or you can just say the following, just using the truth table, you can argue in a more precise way. You can say the following: if you look at the truth table with P, true, false, then not P is false, true, and contradiction is always false. So not P implies contradiction is true, true implies false is false. So this says what? If not P implies C shows up to be true, which is only here, I can conclude that's the only line where that happens, that not P implies C is true. This is not P implies C, contradiction. Then if I read true, then it must be in the line when P is true. So generally that's the reason why it has to work that way, and why we consider this as the correct way to write proof. So here it is. Example 251, statement says, there is no integer which is both even and odd. Both even and odd. So this whole statement is a statement P. So that's our statement P. So instead of proving P, we actually assume not P. What would that be? It's not true that there is such an integer. Not P is there is such an integer. There is an integer which is both even and odd. And then we want to see how will that get us to contradiction, and when we reach contradiction we say, so P itself is true. And then what? Standard way, we do deduction the same. So there is an integer, let n be such an integer. So that means that n equals 2k for some k in z. Why is that? When I say such an integer, that means both even and odd. And then, from the assumption that that number is odd, n equals 12 plus 1. And then, those two must be equal. So we get 2k equals 12 plus 1. Now we get k and l on the same sides. 2 times k minus l is 1. And then this is contradiction. Why? Now we need to argue. Maybe just someone will say, yeah, that's obvious that it's not true. Or we need a little more maybe argumentation. Why would that be contradiction? Because here is the argument I mentioned in the notes, then that number 2 times k minus L, whatever that number is equal, actually 2 times k minus L plus 0. But on the other hand, it is equal, because that's how it looks, it is equal to 1, and as 1 I can write it 2 times 0 plus 1. And now I see contradiction. Why? Because using quotient remainder theorem, when you divide your number by 2, here you get remainder 0, and here you get remainder 1, and we have in that theorem that you can only have the unique quotient remainder representation. So let's say remainder of our number of 2k minus L equals 0 and equals 1, which is contradiction. So here is the simple proof. And then once we reach contradiction, we call this argument by contradiction. So this is arguing by contradiction. Contradiction. And we say, according to the argument by contradiction, P must be true. Or maybe even more, we say we prove that not P implies contradiction, so P must be true. And then in the same way, we proved in the example 252 here we proved that no integer can be at the same time even and odd. On 252, we showed actually that every integer must be one of those. So every integer is either even or odd, never both at the same time. So every integer is either even or odd. But from a minute ago we know it cannot be both. Proof is very easy from proportional remainder theorem. Take n arbitrary integer. And then we use quotient remainder theorem. N equals quotient times 2, I want for d equals 2, for d equals 2, n equals q times 2 plus r, where r is greater or equal 0 and less than 2. But then, what are the integers between 0 and 2? This basically says what? That r is either 0 or r is 1. So generally what are we getting here? N equals 2q or n equals 2q plus 1. That means n is even or n is odd. Very simple. We didn't need to argue here by contradiction. We actually called the old theorem. So now we have side by side two theorems, one saying that every integer is either even or odd, and the other one that it cannot be both simultaneously. And of course your reaction to these two proofs could be, oh, I knew that even before we talked about it, but now this is established according to definitions and we have solid proofs that we can trust seriously, not just, oh, I think I remember seeing something like that there. All right. It says here in example 253, it says if a, b, c are integers and a squared plus b squared equals c squared, then at least one of the numbers a, b, c is even. That's a little much trickier than this. So we are proving the following. So example 3, a, b, c are integers, and a squared plus b squared equals c squared, and then it says at least one of them is even. least one of the integers, A and B is even. The statement P that we need to prove. And we will argue by contradiction. Argue by contradiction. So assume not P. So what is that? Opposite from at least one of them is even, that means none of them is even. So opposite from at least one, none is even. Now what? That means that A is not even, and also B is not even. But then from a minute ago, it's either even or odd, so if A is not even, A is odd. The same way B is odd. So here it is, from negative information we have positive information. Now business as usual, A equals 2k plus 1, B equals 2l plus 1, and then we have the following, see algebra, A squared plus B squared, which is 2k plus 1 squared plus 2l plus 1 squared. Uh-oh, now it's not that obvious that something's wrong here. I don't see that contradiction very easily. But what do you do algebra? 4k squared plus 4k plus 1 plus 4l squared plus 4l plus 1. And then I join expressions that all have 4 and pull out 4. We get like this 4 times k squared plus l squared plus k plus l plus 2. So look what we got. And you see, contradictions are not always that easy and simple. Like, so what's wrong with this? So maybe if I call this S, looks like k squared equals 4s plus 2. And I claim that this is contradiction. Why is that contradiction? Because we know that no square can have 4s plus 2. Why not? That's actually a statement that we should have prepared before this, or our knowledge. And actually that's what in the notes I wrote as a lemma. A lemma is a statement that you prove in order to serve you in the proof of the other statement. So lemma, c squared never has a form 4s plus 2. I wrote it a little better in the notes, but basically that's what it is. Why not? Very simply, c is even or odd. So if c is even, c equals 2k, so c squared is 4k squared, so a remainder of c squared with respect to 4 is 0, because 4k squared, 4 times q plus 0. If c is odd, your c squared is 4k squared plus 4k plus 1. If I call this 4u plus 1, so remainder of c squared when you divide it by 4 is 1. So this actually we will prove something nicer, that the square of an integer, a remainder of c squared, with modulo of when you divide by 4 is either 0 or a remainder of c squared modulo of 4 is 1. It's never 2 or 3. So because the remainders modulo 4 are less than 4, 0, 1, 2, 3. But this tells you if it's a square in action, this cannot happen. It's either 0 or 1. We got here remainder 2, and that contradicts the lemma. And then again, since not P got us into contradiction, then we say according to argument by contradiction, P is true. So it was a little trickier. I don't want to leave you the impression that actually all proof by contradiction are something easy. There's also lots of work and content, but I wanted you to pay attention to the structure of these proofs. All right, let me now show you a couple of more little trickier examples, and then at the end I will talk about the contraposition, so I'll a little bit reorder the section with respect to the way it's written in the notes. Theorem 252. It says square root of 2 is irrational. That's a famous theorem, famous from the Greek times, from the time like 7th, 8th century or 6th, 7th century BC, because Greeks thought that everything that we work with must be rational. And rationality, let me remind you, is, so rational means commotion, M over N. So they thought that every math object, every quantity in the nature is a fraction. But then they came with the square root of 2, and they thought that it's irrational for a long time, and they were extremely surprised to find out that square root of 2 is irrational. And that's one of the most famous proofs in the whole mathematics. So how does this proof go? Actually, we'll argue by contradiction. This is our statement P. So assume and not P. So that means square root of 2 is not irrational. But irrational means not rational, so it's not rational, so square root of 2 is rational. So every number is either rational or irrational. If you